Welcome back, everyone, to Neural Intel's The Deep Dive. Today, we're diving headfirst into the absolutely incredible, sometimes, mind-boggling world of artificial intelligence. We're here to really unpack the technical details, the nuts and bolts, the sheer engineering feats that are driving this revolution forward. And when I say incredible, I really mean it. Just think about this. The cost to run, to query an AI model that's roughly equivalent to GPT 3.5. It dropped from about $20 per million tokens back in late 2022 down to just 7 cents per million tokens by October 2024.
7 cents? That's staggering.
Right, more than a 280-fold reduction in just 18 months. Or, how about this one? AI systems tackling SW bench coding problems. In 2023, they were solving, 4.4%?
Pretty low, yeah.
Jumped to 2024, 71.7% success rate. Just boom.
That kind of velocity, that rapid technical progress is exactly what we're going to dig into today.
Exactly. And our main guide for this journey is the Artificial Intelligence Index Report 2025. It's super comprehensive, very data-driven. This isn't just, a few interesting stories. It's a detailed snapshot, grounded in solid data, covering the whole global AI scene.
Right, from the fundamental research, the technical performance benchmarks everyone's chasing, right up to industry trends and, crucially, the real technical hurdles developers are facing. So our mission today is to really distill the most important technical nuggets, the key engineering insights from this huge report, just for you.
We'll explore the raw advancements, but also the inherent technical challenges and the really fascinating implications of AI's super-fast evolution.
Well, we want to give you a clear, precise picture of where AI stands purely from a technical engineering standpoint and, where that cutting edge is actually headed.
We're focusing squarely on the how and the what of AI's technical progress today. We'll steer clear of the ethics and inclusivity discussions, focusing purely on the tech.
Exactly. So let's dive right in.
And hey, just a reminder, if you want to keep up with the latest AI and ML research papers, definitely check out our webpage. The link's in the bio. Okay, let's kick things off with what really feels like a global AI competition, almost like the Olympics, but with algorithms. The report clearly highlights this fierce international race in AI development. The U.S. is still out front in producing what the report calls notable AI models. They launched 40 in 2024.
40, yeah, compared to China's 15 and Europe lagging a bit with 3.
But, and this is where it gets really interesting from a technical perspective, China is closing that performance gap incredibly fast on major benchmarks.
That's the striking part. How quickly China has gone from, double-digit performance differences just a year earlier in 2023 to achieving near parity in 2024 on really critical benchmarks. We're talking MMLU.
Which tests broad language understanding reasoning.
Exactly. And human eval, which is laser-focused on coding ability. So it's not just about the sheer number of models being put out, it's about the technical capability, the sophistication of those models catching up.
And China also leads in AI publications and patents, right?
Yeah.
Which suggests a pretty robust research engine humming underneath.
Definitely points to a strong underlying research ecosystem.
So let's unpack that term, notable AI models. What does that actually mean in terms of, say, real-world deployment or actual foundational breakthroughs? And technically speaking, what strategies are allowing China to close this gap so quickly? Is it specific architectural tricks? Is it just massive data access or brute force compute scaling?
Or maybe a combination.
Yeah. And how does having more publications and patents really translate into better performance on these specific benchmarks like MMLU and human evil?
Okay, great question. So notable models, Epoch AI, who contributed a lot to this report, defines them as landmark models. They're chosen based on importance, relevance, uniqueness in the field. So these are the models really pushing the state of the art, the ones influencing what comes next.
Gotcha. The trendsetters.
Exactly. Now, as for China, closing the technical gap so fast, the report doesn't give us a secret sauce recipe. No specific architectural breakthroughs are named. But that consistent lead in publications and patents, that points to a really deep, sustained investment in fundamental R&D and intellectual property.
So a big pool of talent, basically.
A large pool of highly skilled AI researchers and engineers, yes. Combine that with potentially significant government-backed compute resources and, crucially, access to vast internal data sets. When you have that high volume of new research, plus the muscle to train huge models, you're naturally going to see performance climb. It implies, a technical maturation in their whole model development pipeline. They're getting better at optimizing existing architectures, refining training processes.
Squeezing more out of the data and compute they have.
Precisely. It's that powerful mix of foundational science and solid engineering execution.
So thinking ahead, what does this converging performance landscape mean? Are we going to see more collaboration, more open research? Or is this competition going to push everyone towards more proprietary, closed-off models, especially with countries vying for that technological edge?
That's a really critical dynamic to watch. And interestingly, the trend the report highlights later actually leans towards less transparency, not more.
Oh, really?
Yeah, a significant chunk of these notable models, even if they release the model weights the parameters themselves,
Oh.
they're holding back the training code.
The recipe.
Exactly, the how-to guide. This strongly suggests a move towards more proprietary development, especially for those frontier cutting-edge models.
Yeah.
If the key innovations, the training techniques, aren't fully open source, it could definitely lead to more parallel, siloed development efforts globally.
Which could maybe slow down collective progress in some ways.
Potentially, yeah. Or, conversely, it might spur even greater domestic innovation as nations feel they need to build their own capabilities independently. Finding that balance between open research and protecting proprietary development is going to be a major technical and, frankly, geopolitical issue in the next few years.
Definitely something to keep an eye on. Okay, let's switch gears to the economics, the engine driving so much of this, cost reductions and hardware power. You mentioned that incredible cost drop right at the start, querying an AI model, dropping from $20 per million dollar tokens down to just 7 cents with Gemini 1.5/8B,
Okay.
over 280 times cheaper in 18 months.
Okay, yeah, let's break that down. A token, just to clarify for everyone, it's the basic unit the AI processes. Think of it roughly like a word or part of a word. So a million tokens is roughly like processing a million words of input or output.
Okay.
And this huge drop is specifically in inference costs. That's the cost of actually using the trained model, not building it.
Right, the running cost.
Exactly. And that reduction is profoundly significant. It completely changes the economic equation for building AI applications.
How so?
Well, imagine if using Google search cost you $20 every time. And now it's effectively pennies for a similar AI interaction. This just throws the doors wide open. It makes powerful AI accessible to way more developers, smaller businesses, startups. It really democratizes access.
So AI stops being just a premium add-on feature.
Precisely. It can become this invisible, almost commodity layer embedded in basically everything. Think about software interactions, smart devices. They can all potentially have a sophisticated AI brain now because the ongoing cost is becoming almost negligible.
Wow. Okay, what does that do to the competitive landscape then, beyond just making AI accessible?
It shifts the value proposition significantly. The race isn't just about having the biggest model or the most compute anymore. It's increasingly about smart data curation, super efficient model architectures, and finding clever ways to embed intelligence at the absolute lowest cost.
So efficiency becomes king.
Efficiency and application, we're already seeing moves towards hyper-personalized AI becoming standard. And even fully autonomous AI agents that can run constantly without racking up huge bills, that becomes feasible now.
And it's not just the cost of using AI that's dropping. The report details these continuous, frankly, mind-bending improvements in the underlying hardware, too. Machine learning hardware performance measured in FLOPs, specifically 16-bit floating point operations per second, growing 43% annually, doubling every 1.9 years.
But really?
And price performance improving 30% per year, energy efficiency up 40% annually.
Yeah.
They give the example of the NVIDIA B100 being nearly 34 times more energy efficient than the P100.
Yeah, the efficiency gains are huge.
So how do these hardware improvements directly translate into bigger models, training on more data? And what about the flip side? These massive power consumption figures, like Paul-M using 2.6 million watts, Llama 3.1405B hitting 25.3 million watts, compared to the original Transformers 4500 watts. That's just astronomical growth in power draw.
Right. So FLOPs, think of that as the raw horsepower of the AI chip, how many calculations it spits out per second. Billions, trillions now. And those different precision types, FP32, TF32, FP16, BF16, think of it like choosing the level of detail. FP32 is like a full high-res photo, super precise numbers, crucial when you're training the model where tiny errors can add up, but it's slower.
Okay.
FP16 or BF16 are more like quick sketches, less numerical detail, but way faster and use much less energy. Perfect for inference for just using the trained model. The big technical trick is we're getting much better at using these lower precision formats effectively, which gives huge speed-ups and energy savings for many AI tasks.
So faster calculations, lower precision where possible.
Exactly. And these hardware boosts directly enable scaling because more FLOPs mean you can process way more data in parallel, run more complex calculations faster. That lets you train bigger models with more parameters on bigger data sets in a reasonable time frame.
The power consumption.
Right, that's the catch. Despite the amazing gains in energy efficiency per calculation, the sheer scale of these modern models means the total power consumption is still going through the roof. Those numbers you cited, 4,500 watts for Transformer, 2.6 million for Pol-M, 25.3 million for Llama 3.1, it shows this exponential leap in absolute power draw.
Which creates huge engineering problems.
Huge technical challenges, yeah.
Yeah.
Data center infrastructure, massive cooling systems to get rid of all that heat and, the overall environmental footprint. And the report also flags network bandwidth as a growing bottleneck as models get distributed across more and more chips.
It's not just how fast each chip computes.
Exactly. It's how fast they can talk to each other, share data. That communication speed is increasingly limiting how fast you can train these massive distributed models.
That's a staggering amount of power. So are there limits? Theoretical or practical limits to these hardware gains? And how will that focus on network bandwidth, the communication bottleneck shape future AI hardware design?
Theoretically, well, there are always fundamental physics limits, right? Speed of light, thermodynamics, dissipating heat. Practically, yes, energy consumption and heat are becoming massive constraints right now. We're hearing about companies seriously looking at, dedicated nuclear power for future AI data centers. That's the scale we're talking about.
Oh.
And the shift towards prioritizing network bandwidth means future chip designs will likely integrate high-speed communication links much more tightly with the processors. Maybe more on-chip memory, faster interconnects, trying to minimize the delay and maximize the data flow between compute units.
So less focus on just raw FLOPs, more on communication efficiency.
It could lead to specialized chips optimized for that communication-heavy parallel processing, yeah. Because if the data can't get to the processor fast enough, all that raw compute power just sits idle. It's wasted.
Okay, let's shift to data, another huge piece of the puzzle. This is something keeping a lot of AI folks up at night. The evolving data landscape. The report stresses how heavily models rely on massive public web data for training. But, and this is the crucial part, data use restrictions shot up significantly between 2023 and 2024.
Yeah, that's a big one.
The proportion of restricted tokens in the C4 Common Crawl dataset, a big web scrape, jumped from maybe 5-7% up to 20-33%. That's a huge chunk suddenly becoming off limits.
And Epoch AI, the research team tracking this, they estimate we might actually burn through the current stock of usable training data, including the entire indexed web sometime between 2026 and 2032.
Wait, run out of data?
Yeah.
Actually run out.
It's a fascinating and, slightly alarming prospect, at least for the kind of public web data we've relied on. Just to clarify again, tokens for training data are those basic units, words, parts of words. The scale is immense. Original Transformer,
Wow.
2 billion tokens. GPT-3, 374 billion. Llama 3.3, around 15 trillion tokens.
15 trillion.
And these LLM training data sets are doubling roughly every 8 months. So you have this exponential growth in data appetite colliding with a sudden increase in restrictions. That creates a major technical challenge for future model growth. It limits data diversity, impacts model alignment, making sure it behaves properly, and potentially caps scalability.
So if this public data commons is shrinking, how does that technically hold back future model development? Does it mean models just become less diverse or hit a performance wall sooner because there's no fresh data?
It has several really profound technical consequences. First, data diversity is key for generalization, right? For models to work well on new stuff and avoid bias. If they're trained on narrower, less diverse data sets because of restrictions, they might struggle outside their training distribution, become brittle. Second, alignment. If the available data is less representative of the real world's complexity, getting models to align with human values or intentions gets technically harder. And third, scalability. If the current paradigm relies on more data equals more capability, then a data bottleneck could constrain model growth, maybe lead to diminishing returns on just throwing more compute at the problem.
Which forces a rethink on the data side.
Exactly. It forces a technical shift, pushes towards finding new solutions.
And the report points to synthetic data as one potential solution here. Now, I remember earlier research suggested this idea of model collapse if you trained only on synthetic data.
Right, the quality degrades over generations.
But newer research, the report says, shows that layering synthetic data on top of real data seems to prevent this collapse. So first, what's the technical mechanism behind model collapse? How does it actually happen?
Model collapse is a really interesting, kind of scary technical phenomenon. When you train models only on data generated by other AI models, they tend to lose the less common stuff, the tails of the data distribution. Imagine making photocopies of photocopies eventually. The image gets degraded, loses detail.
Okay, makes sense.
It's similar here. The models trained only on AI output start to forget the rare nuances, the exceptions, the complex edge cases that were in the original real data. They become less diverse, output quality degrades, factual accuracy can plummet. It's like the AI's knowledge base just gets shallower and shallower with each synthetic generation.
So the layering approach, using synthetic data to augment rather than replace real data, how does that technically fix it?
By keeping the real data in the mix, you anchor the model to the original, richer distribution. The synthetic data adds more examples, maybe helps generalization in some areas, but it doesn't completely overtake the foundational knowledge learned from the diverse real-world data. It preserves that full spectrum.
But generating good synthetic data must still be hard, right? What are the technical challenges there, making sure it's not just replicating the same patterns or biases?
Oh, absolutely. That's a huge technical challenge. If your synthetic data just mirrors the patterns, and crucially, the biases already present in your real seed data, you're not really solving the diversity problem. You might even be amplifying existing biases just faster.
Right, garbage in, synthetic garbage out.
Kind of, yeah. The goal is to generate synthetic data that's genuinely novel, diverse, and high quality enough to actually improve the model without introducing new errors or just causing the model to overfit to the combined dataset. This requires incredibly sophisticated generative models themselves, ones that can capture complex data distributions and maybe even invent new, plausible examples that go beyond simple interpolation.
So we might see new learning approaches emerge because of this data pressure.
Very likely. Maybe more focus on transfer learning, few-shot learning, getting models to learn effectively from much less data, or architectures specifically designed for data efficiency. It's a major driver for innovation.
Let's pivot now to AI agents and the open source software landscape. Agents are fascinating AI, moving from just responding to actually doing things. The report highlights early promise here. There's a new benchmark, RE-Bench, launched in 2024, specifically for evaluating complex multi-step tasks.
Right, testing these agent capabilities more rigorously.
And the results are intriguing. Top AI systems apparently score 4 times higher than human experts in short bursts like a 2-hour task budget.
What then?
But then, give them a longer time horizon, say 32 hours, and human performance flips, surpassing AI 2 to 1.
Interesting dynamic. Suggests AI is good at focused sprints, but maybe struggles with longer-term strategy or adaptation.
Could be. Yet on the other hand, the report says AI agents already match human expertise in very specific complex tasks, like writing Triton kernels, these super optimized GPU programs, and doing it faster and cheaper.
That Triton kernel example is significant.
And they mention OpenAI's O1 and O3 models, showing advanced reasoning, using chain of thought, and iterative checking.
Okay, so let's define an AI agent technically. It's not just a chatbot answering questions. It's an AI system designed to autonomously interact with an environment, right?
Yeah.
It perceives, it plans, it takes actions, it pursues goals over multiple steps. It's like giving the AI hands and an objective.
So it can manage your calendar, code software, control a robot.
Exactly. It's built to do things, not just talk, using tools, remembering past steps, refining its approach, all to achieve a goal.
And chain of thought. How does that technically work?
Chain of thought is a really clever technique. Instead of the model just blurting out a final answer, you prompt it to articulate its reasoning process step by step. It literally writes out its thought process, which seems to help it arrive at more accurate answers for complex problems and makes its reasoning more transparent and checkable. You can see how it got there.
And the significance of matching humans on writing Triton kernels. That sounds highly specialized.
It is. Triton is a language for writing extremely optimized, low-level code that runs directly on GPUs for maximum performance, often used in machine learning itself. It's a complex, niche programming task requiring deep understanding of parallel computing and hardware. An AI agent doing this effectively means automating highly technical, performance-critical coding.
Which could massively speed up development cycles for ML workload.
Exactly. And automate optimization. The report also mentioned OpenAI's O1 hitting 97.8% zero shot on a planning benchmark called Bloxworld, vastly better than other top models. Shows a real leap in complex planning for these agents.
Okay, so they're great at specific tasks. Chain of thought reasoning is improving.
Yeah.
Why do humans still beat them over longer time horizons? What's missing technically?
It likely points to limitations in things like maintaining coherence over long interactions, robustly managing internal state or memory, and maybe adapting to unexpected changes that require genuine world understanding, not just logical steps.
So common sense and flexibility.
Pretty much. Humans have a richer internal model of the world, allowing for more flexible long-term planning, improvisation, and recovering from errors in ways AI struggles with. For AI agents to get better at long-horizon tasks, the next technical breakthroughs probably need to involve better long-term memory systems.
So they can recall and integrate info over time.
Right. More robust self-correction loops that go beyond just logic, adapting to new information, better hierarchical planning, maybe more sophisticated internal simulation capabilities to predict long-term outcomes.
And maybe bridging that gap between pattern recognition and explicit logic.
Yeah, combining neural approaches with more symbolic reasoning could be key for that kind of robust long-term problem solving.
Now let's touch on open source AI. GitHub stars for AI projects are booming 14 million in 2023, up to nearly 18 million in 2024. Huge community interest.
Massive growth, yeah. Shows broad engagement.
The US leads in projects, but India and Europe are right behind. But here's that point we touched on earlier, tying back to proprietary models. In 2024, over 60% of these notable AI models were launched without their training code, even if the model weights were released.
Yeah, this is that critical distinction. Open weights versus fully open source. Open weights means you get the model's parameters, the trained brain, basically. You can run it, use it, often fine-tune it.
Which is great for accessibility applications.
Definitely. But fully open source means you also get the training code, the data prep scripts, the whole recipe. And withholding that training code creates a real barrier to full reproducibility and deep technical understanding.
Why is that so important technically?
Without the training code, it's incredibly hard for other researchers to know exactly how the model was built, replicate the process, identify potential flaws or biases introduced during training, or confidently build upon that specific foundational work.
So it limits scrutiny and certain kinds of collaborative research.
Exactly, the kind of deep, open collaboration that often drives rapid progress. It makes it harder to verify claims or compare models rigorously.
So how might this lack of open training code actually slow down broader technical progress? Does it inevitably push towards more closed ecosystems?
It certainly creates more of a black box situation, even if you can use the model. Understanding the why behind its behavior or how best to adapt its training for new areas becomes much harder. This can slow down foundational research and make it riskier to build complex systems on top of these partially opaque models.
And it probably incentivizes keeping data and methods secret too.
It definitely encourages a shift towards more proprietary internal datasets and training techniques being guarded as competitive advantages. This could lead to a more fragmented AI landscape. On the flip side, it could also supercharge research into things like advanced data synthesis or new transfer learning methods that need less original training data, specifically to try and overcome these data and transparency barriers. It's a complex dynamic.
All right, let's shift focus to the raw technical performance we're seeing across key areas, starting with language understanding and generation. AI mastering new benchmarks faster than ever seems to be the story. That SWB bench coding example again, 4.4% to 71.7% success in 1 year.
Just an incredible leap in coding ability.
And on other tough ones like MMMU and GPQA, the report cites gains of nearly 19 and almost 50 percentage points respectively. Big jumps.
So technically what this tells us is the bar for AI performance keeps getting raised, and the models are vaulting over it with surprising speed. These benchmarks, MMMU is massive, covering tons of subjects, multimodal too. GPQA is tough, general knowledge. They're designed to push AI beyond just memorizing facts.
They require real reasoning.
Deep understanding, logical inference, complex problem solving. The rapid gains show that current scaling approaches, combined with architectural tweaks like chain of thought and better training, are still yielding major improvements.
But we haven't solved it all yet.
Oh, definitely not. The report mentions newer, even harder benchmarks continually popping up. Humanity's last exam top AI gets less than 9%. Frontier Math AI solves only 2% of the problems.
Wow, okay. So still a long way to go for truly complex, human-level reasoning.
Absolutely. There's a vast frontier still to explore there.
The report also mentioned something interesting. Performance at the very top,
Right.
the frontier models, seems to be converging. Multiple companies now offer models that are highly capable and pretty close in performance.
Yeah. That's technically significant, like Google's Gemini models doing well on the chatbot arena leaderboard.
Which is based on human preferences, right?
Exactly. And OpenAI's GPT-4o, that's their new multimodal model handling text, audio, images, video altogether, responding to audio in just 320 milliseconds.
That's incredibly fast for audio interaction.
It's a huge feat for low-latency natural interaction. Then you have Alibaba's Qwen 2 rivaling models like Llama 370B and Databricks DBRX, that huge mixture of experts model.
Okay, so convergence implies maybe the core techniques are becoming well understood.
It suggests certain architectural patterns like the transformer, and scaling methodologies are proving effective across different teams. It's not just one dominant player pulling away. And that multimodality in GPT-4o is a massive technical leap, processing and generating across text, audio, image, video in one unified model.
How does that work architecturally?
It requires a really deeply integrated representation space inside the model where information from different senses basically can interact and influence processing rather than having separate pipelines. That 320 meters audio response time is also a testament to incredibly optimized inference.
Mixture of experts, MOE, like in DBRX. You mentioned that's exciting.
Hugely exciting. DBRX has 132 billion parameters total, but apparently only activates about 36 billion for any given input. How? It uses a special gating network that intelligently routes the input to a small subset of expert subnetworks specialized for different tasks or data types.
Ah, so you get the knowledge capacity of a huge model.
But the computational cost during inference is much lower, closer to a smaller model, because you're only running a fraction of it each time. This balance between massive scale for knowledge and practical efficiency for usage is a key technical focus right now. It's a path to even bigger, smarter models without impossible running costs.
Very clever. So looking beyond just crushing academic benchmarks, what are the next big technical frontiers for these large language models? Where does the focus shift for real-world use?
Yeah, good question. Beyond benchmarks, the big technical hurdles are improving factual grounding, making absolutely sure the models aren't just sounding plausible, but are reliably accurate and verifiable. That's huge.
Avoiding hallucinations.
Exactly. Also, enhancing long-term memory and statefulness so they can have truly coherent, extended conversations or interactions, remembering context from way earlier.
Oh, wow.
And improving their ability to handle really complex and multi-step reasoning that isn't easily prompted step by step.
So robustness in the messy real world.
Precisely. Dealing with noisy or ambiguous instructions, understanding subtle user intent, resisting attempts to trick them adversarial attacks. The rise of benchmarks like WildBench, which uses messy, challenging real-world queries, really signals this critical shift towards measuring practical utility and robustness, not just academic scores.
Makes sense. Okay, let's talk visuals. Image and video generation have seen some truly mind-blowing progress. The Visual Common Sense Reasoning Benchmark, VCR, the report says, AI used to really struggle with this, but in 2024, a model finally matched the human baseline score of 85%.
That VCR benchmark is tough because it's not just about recognizing objects, it's about understanding the why and how in an image, the implicit relationships, intentions, cause and effect.
Like knowing someone is about to throw a ball, not just seeing a person and a ball.
Exactly. That requires common sense reasoning about the visual world. Models hitting human levels likely use very sophisticated visual linguistic pre-training. They learn rich connections between visual patterns and abstract concepts from huge data sets of images paired with detailed text descriptions. Architecturally, probably powerful vision encoders linked to large language model decoders, letting them reason about what they see. It's a major step towards real visual intelligence.
And just looking at image generators like Midjourney, the improvement from 2022 to 2025 is astonishing. The report uses a hyper-realistic Harry Potter prompt example, going from, quote, cartoonish and inaccurate renderings to startlingly realistic depictions.
That rapid improvement reflects continuous technical breakthroughs in the underlying generative models, especially diffusion models and maybe advanced GANs. Key improvements are things like much higher output resolution, better understanding of complex prompts so the AI gets what you're asking for, and more sophisticated techniques to generate photorealistic details, textures, lighting, expressions, while keeping the image coherent.
They're getting scarily good at mimicking reality.
The fidelity and artistic control available now are just worlds apart from even 2 years ago.
And video generation is heating up fast too. Meta, Google, OpenAI all have major players now. Meta's Movie Gen can do instruction-based editing, add sound. Google's VO models apparently outperform others internally. OpenAI's Sora generating incredibly realistic scenes.
Video is way harder than static images, technically speaking. You need coherence over time, maintaining object identity, consistent motion, believable interactions across dozens or hundreds of frames, often at high resolution like 1080p, and standard frame rates. That's complex. Movie Gen hitting 16 seconds at 16 fps, 1080p is already impressive.
What are the architectural tricks for video?
It often involves extending techniques like diffusion into the time dimension, using architectures like spatiotemporal transformers that can reason about how things change frame to frame and maintain that consistency. Adding sound, allowing editing via instructions that requires even more sophisticated multimodal integration and control mechanisms. The computational cost is also significantly higher than for images.
Given these rapid advances, what are the next big technical hurdles for video generation? What's the dream goal here of generating a whole movie?
Pretty much. The current challenges are definitely generating longer, more complex videos with true interactivity or fine-grained control. We're far from generating a feature film or, say, a dynamic video game environment with consistent physics and character control over long periods. So the next technical frontiers are improving that long-range temporal consistency, making sure things look and move right over minutes, not just seconds, enabling precise user control over characters, objects, camera angles within the generated scene, and doing all this efficiently at very high resolutions.
Maybe breaking it down. Generate a plot, then scenes.
Yeah, hierarchical generation is a likely path. Maybe even integrating real-time physics engines to ensure the generated motion is physically plausible. It's a massive, multifaceted engineering challenge.
Let's move into the physical world now. Robotics and autonomous motion. 2024 really felt like the year of the humanoid robot, right? Figure AI's Figure O2, Tesla's Optimus, Boston Dynamics' new Atlas.
Definitely a lot more focus and impressive demos.
Figure O2 specs are pretty impressive. 5'6", 154 pounds, 44-pound payload, 5-hour runtime, and doing complex stuff like making coffee, helping on an automotive line.
The hardware is advancing quickly.
But the really interesting part, technically, is the integration with OpenAI for speech-to-speech reasoning.
Yeah, that's key. Building stable, dexterous humanoid robots that can navigate messy human environments is incredibly hard already. Balance, walking, fine motor control, safety. Integrating sophisticated language models like OpenAI's allows for much more natural interaction. The robot can understand spoken commands, explain what it's doing, answer questions.
So it's not just following pre-programmed routines.
Exactly. It moves towards more adaptable, intelligent physical action based on high-level linguistic instructions. It gives the robot a brain that can translate language into precise physical movements in real time.
Then there's Google DeepMind's Aloha, unleashed, getting robots to do really intricate stuff like tying shoelaces, folding t-shirts.
Tasks that require incredible dexterity.
And they achieve this using large imitation learning datasets combined with transformer architectures. Plus this technique called SARA, self-adaptive robust attention, reducing computational demands for robotics transformers.
Right. Aloha is fascinating because it tackles tasks that were almost impossible for robots just recently. Handling fiddly things like shoelaces or deformable objects like clothes requires amazing precision and touch sensitivity. The technical approach uses imitation learning. The robot learns by watching lots of human demonstrations.
Learning by watching.
Yeah, and combining that with transformer architectures, which are great at understanding complex sequences, allows the robot to generalize those skills to new situations, not just perfectly copy the demos.
And SARA. How does that help?
SARA is a really significant technical optimization. Standard transformers, used everywhere now, have a computational cost that grows quadratically with the length of the input sequence. Double the input, quadruple the compute. That gets expensive fast for robots processing lots of sensor data over time.
Right.
SARA cleverly changes the internal attention mechanism so the complexity scales linearly instead of quadratically. Double the input, only double the compute.
That sounds like a massive efficiency gain.
It's huge. It means robots can process much longer streams of sensor data, make faster decisions, using sophisticated AI control without needing a supercomputer strapped to their back. Makes advanced AI feasible on mobile platforms.
So looking ahead for robotics, what's next beyond just imitation learning? And can SARA get even more efficient?
The next big step is reducing the reliance on massive human demonstration data sets for imitation learning. More focus on reinforcement learning, letting robots learn through trial and error with maybe sparser rewards from humans. also developing better world models inside the robot so it can predict the consequences of its actions without needing to see every possibility demonstrated.
More independent learning.
Exactly. As for Sarah, converting to linear complexity is already a massive win. Further gains might come from optimizing that linear process even more, or specialized hardware designed explicitly for these linear time transformers. But the biggest hurdle was getting past that quadratic scaling.
Finally, in this section, autonomous driving. Waymo's progress is remarkable. Over 20 million rider-only miles in Phoenix by Sep 2024.
That's a lot of real-world, no safety driver miles.
And consistently lower rates of airbag deployments, injury crashes, police-reported incidents compared to human drivers in those areas.
Those safety stats are the key technical validation. Achieving that level of safety consistently suggests incredibly robust perception, prediction, and planning systems. Waymo uses a suite of sensors, LiDAR, radar, cameras fusing that data for a comprehensive, redundant view. Their perception systems need near-perfect object identification, and prediction has to anticipate what other road users might do.
Making safer decisions than humans, statistically.
That's the goal, and the data suggests they're achieving it in their operating domains. Of course, the technical hurdles for wider deployment, complex cities, tricky weather, truly unpredictable human behavior are still substantial, handling all the long-tail edge cases.
And China's self-driving scene is exploding too. Baidu's Apollo Go reporting nearly 1 million rides in Q3 2024, aiming for 1,000 robotaxis soon. And they're affordable.
Yeah, China is moving very aggressively in deploying autonomous ride-hailing services, often at scale and with competitive pricing. It's a different operational environment, but the technical push is immense there as well.
You mentioned Waymo's safety relies on robust systems. What kind of data and simulation is needed for that? And what are the big technical challenges in scaling fleets up to thousands of vehicles?
It's a combination of massive real-world driving data, absolutely critical. But equally important is extensive high-fidelity simulation. They can run billions of virtual miles in simulation, testing countless scenarios, including incredibly rare edge cases, safely and quickly. They can replay real-world incidents, find root causes, fix the software, test it again virtually, all before deploying to the fleet.
Continuous virtual testing.
Exactly. Scaling to thousands of vehicles brings a whole new set of technical challenges beyond the car's AI, managing the colossal data streams from the entire fleet.
Terabytes per car per day, right, easily.
Optimizing routing and dispatch in real time for a huge fleet. Keeping high-definition maps constantly updated across vast areas. Securely managing software updates over the air for thousands of vehicles. The back-end infrastructure, data ingestion, processing, model retraining pipelines becomes a massive technical undertaking in itself, just as complex as the driving AI.
Okay, let's shift to how AI is transforming specific fields, starting with science and medicine. A report highlights a surge in large-scale medical foundation models in 2024, from general-purpose multimodal ones like MedGemini to really specialized models. EchoCelie for heart scans, VisionFM for eyes, ChecksAgent for X-rays.
Right, a foundation model in medicine is similar to general LLMs, a huge model pre-trained on vast amounts of diverse medical data. Text from health records, images like X-rays or MRIs, maybe genomic data. They can then be adapted for specific tasks. Diagnosis, predicting outcomes, planning treatments. The modality is key, integrating insights from images, text, numbers like a doctor does, but potentially seeing patterns across millions of patients.
Enhancing diagnostic power.
Potentially, yeah. But the technical requirements are huge. You need massive amounts of high-quality, often very private medical data, and the models need to be robust, reliable, and critically interpretable enough for doctors to trust them in clinical settings.
Makes sense. In biology, we're seeing huge growth in public data to protein databases like UniProt, AlphaFold.
Providing fuel for AI-driven discovery.
And AI is accelerating discovery itself. Models like Aviary, using LLM agents for biotasks. Firesat predicting wildfires. OpenAI's O1 model nearly maxing out the MedQA medical exam benchmark.
That MedQA result is impressive. Shows strong medical knowledge recall and reasoning.
But this Stanford Virtual AI Lab example is wild. Multiple LLM scientists collaborating to design nanobodies against SARS-CoV-2, with over 90% success in binding.
Yeah, that Stanford example really shows the paradigm shift. AI moving from just a tool analyzing data to an active collaborator or even autonomous agent in research.
Yeah.
Technically, that virtual lab involves multiple LM agents, each maybe role-playing a different scientific specialist, an immunologist agent, a computational biologist agent, etc. They autonomously chat, propose hypotheses, design virtual experiments, analyze simulated results, critique each other, and iterate, all within a simulated environment.
Like a virtual research team.
Exactly. And achieving over 90% success in designing functional nanobodies demonstrates their technical capability to navigate complex biological problems and generate real scientific leads with minimal human guidance. It's a glimpse of potentially autonomous science.
And there's Gluformer, analyzing continuous glucose monitor data, predicting long-term health risks years in advance.
Right. Gluformer is a foundation model trained on CGM data streams. It learns subtle patterns in glucose fluctuations over time, how levels respond to food, exercise, stress patterns that might predict future risk of diabetes or heart problems maybe 4 years out. Technically, it uses time series analysis, probably transformers or RNNs, to find these predictive signals in noisy, continuous data. Something very hard for a human doctor to spot just by looking at charts.
That's incredible predictive power. How exactly does it analyze that continuous data stream? And what are the technical limits right now for fully autonomous AI science? Can these virtual labs be scaled?
Gluformer likely uses architectures adept at sequences, learning long-range dependencies in the glucose readings, identifying maybe specific shapes of glucose curves after meals, or overnight variability patterns that correlate strongly with future health outcomes learned from a massive patient data set. It's complex physiological pattern matching over time. As for limitations to autonomous science, AI is still fundamentally bound by the data and knowledge it's trained on. Generating truly novel, out-of-the-box hypotheses that go beyond current paradigms or designing experiments requiring real-world intuition, that still seems largely human.
So creativity and intuition are still key differentiators.
For now, yes. Scaling these virtual labs involves technical challenges in integrating more diverse virtual tools, managing complex agent interactions, and ensuring the AI critics are robust. Generalizing to other fields needs domain-specific data and maybe new specialized agents, but the core autonomous collaboration framework is powerful.
Let's look at physics and quantum computing. Oak Ridge National Labs orbit model 113 billion parameters, hitting 1.6 exaflop/s for climate science.
1.6 exaflop/s, that's 1.6 quintillion calculations per second. Just staggering compute power needed for those incredibly complex climate simulations. Orbit is apparently 1,000 times larger than prior climate models.
And Neural GCM combines physics rules with machine learning for weather climate.
Yeah, these hybrid models are interesting. They use known physics equations as a backbone, grounding the machine learning components. This can make simulations more efficient, accurate, and stable than purely data-driven ML models, especially for long-term predictions. Best of both worlds.
Then in quantum, Google DeepMind's AlphaQubit and Willow are pushing the state-of-the-art in error correction. Willow completed a task in minutes that take a supercomputer 10 septillion years.
Okay, that Willow result is mind-bending. It relates to quantum error correction. Qubits are super fragile, prone to errors. Fixing errors is crucial, but often the fixing process itself introduces more errors. There's this concept called the surface code threshold, a point where error correction becomes counterproductive. Willow achieving error suppression below this threshold is a monumental technical milestone.
What does that mean practically?
It means they found a way to make the error correction work so well that it actually stabilizes the system dramatically. It implies we might be able to build reliable, fault-tolerant quantum computers with far fewer, less perfect physical qubits than previously thought.
Making practical quantum computing closer.
Potentially much closer. It opens the door to tackling those kinds of currently impossible problems, like the one Willow solved so quickly. It's a fundamental physics breakthrough for the field.
So what's the next technical step needed to make quantum computers practical for broader science, beyond these specific, amazing demonstrations?
The next big hurdles are scaling up the number of high-quality, stable qubits, making them stay coherent, maintain their quantum state for longer, and developing even better error correction codes. Plus, building out the whole software stack, quantum programming languages, compilers, algorithms to actually use these machines effectively for a wide range of scientific problems. It's still a massive engineering challenge across hardware and software.
Let's switch to AI's impact on productivity and the workforce. The report has some striking numbers here. AI adoption boosting customer support agent productivity by over 14%. Scientists using AI seeing a 44% increase in materials discovery rates, nearly 40% increase in patent filings.
Those are significant productivity gains.
A Microsoft study found AI automation reduced perceived mental load by 45%, closed 84% of the accuracy gap for non-native English speakers. and AI projects needed almost 80% fewer collaborators.
Wow. What's clear here is AI acting as a powerful amplifier of human productivity, not just replacing tasks wholesale. Technically, it achieves this by streamlining things. Faster info access for support agents, automating tedious literature reviews or data analysis for scientists, drafting text, suggesting code.
Taking cognitive load off.
Exactly. Reducing mental demand, improving communication clarity, like for non-native speakers.
Right.
It augments human capabilities. The reduction in collaborators suggests AI can consolidate tasks previously needing multiple people.
The report also notes a fascinating shift in how scientists spend their time. Idea generation down from 39% to 16% of their hours.
Because the AI can generate lots of ideas quickly.
Seems like it, but judgment tasks, evaluating those ideas, making decisions increased from 23% to 40%. And the key factor for positive impact was the human ability to effectively evaluate the AI's suggestions.
That's a really profound insight into the changing nature of skilled work. AI takes over the initial brainstorming or solution generation, freeing up humans for the crucial higher-order tasks: critical evaluation, synthesis, validation, strategic decision-making based on the AI's output. Judgment becomes paramount.
So technically, what do AI tools need to do to support that judgment role effectively?
They need to be more transparent and explainable, not just give an answer, but show their work, provide confidence scores, highlight the supporting data, maybe explain their reasoning path. Future tools will likely need better mechanisms for critique, explanation, and interaction to truly enhance human judgment.
How else might AI reshape technical job roles and skills? And what technical features could boost that human-AI collaboration on judgment?
We'll likely see a continued shift away from routine tasks towards skills like complex problem framing, critical evaluation of AI outputs, prompt engineering, AI model interpretation, data curation for AI, AI auditing.
More meta-level skills around managing and interacting with AI.
Exactly. To enhance collaboration for judgment, future AI tools could offer features like interactive what-if simulations based on their recommendations, visualizations of their decision process, maybe adaptive feedback loops where human critique directly improves the AI's future suggestions.
Like an AI that knows what it doesn't know and asks for expert help.
Precisely, making the interaction more of a dialogue, a true collaboration between human expertise and AI's computational power.
Okay, let's tackle the crucial area of responsible AI, focusing on the technical side of the challenges and progress. The report paints a picture of an ecosystem evolving unevenly. AI-related incidents are rising sharply, 233 reported in 2024, up over 56% from 2023.
That's a significant jump in reported problems.
Yet standardized responsible AI evaluations are apparently still rare among the big industrial model developers, though new benchmarks like Helm safety and AirBench are starting to emerge.
Yeah, this raises that critical technical question. AI is advancing like crazy, but how are we technically measuring and mitigating the risks? Defining and measuring responsible AI for these complex, adaptive, often non-deterministic systems is technically very hard. Traditional software testing just doesn't cut it.
Why not?
Because these systems can have emergent behaviors, unpredictable responses that weren't explicitly programmed. You can't just test known inputs and outputs. Benchmarks like Helm safety and AirBench are attempts to standardize this. Technically, they involve things like generating specific adversarial prompts designed to trigger bad behavior, or evaluating outputs against predefined safety criteria, toxicity, bias, factuality, often using other AI models to help automate the scoring.
Trying to create a more systematic, data-driven way to assess safety profiles.
Exactly. And the rise in reported incidents, while worrying, might also reflect better awareness and reporting within the tech community, not just more problems occurring.
So technically speaking, what's needed to get truly standardized RAI evaluation across different types of AI, language, vision, robotics?
It likely needs a combination of things: robust, auditable datasets specifically designed to probe for failures and biases, more sophisticated automated evaluation agents that can simulate diverse real-world interactions and detect subtle issues, more transparency and standardized reporting from developers on their testing methodologies and results, and benchmarks that work across modalities testing safety consistently, whether it's text, images, or robot actions.
And maybe understanding why they fail.
Yes, huge emphasis on explainable AI, XAI techniques, and even formal verification methods to understand the root causes of undesirable behavior, not just detect it after the fact.
Let's zoom in on implicit bias and factuality in language models. The report is pretty blunt. Even advanced LLMs like GPT-4, Claude 3, despite efforts to curb explicit bias, still show implicit biases.
Yeah, the subtle stuff that's harder to catch.
Examples like associating negative terms more with black individuals, women with humanities not STEM, men with leadership roles. Identified using new technical methods, LLM implicit bias and LLM decision bias.
Right, the technical distinction is key. Explicit bias is often tackled with content filters, safety prompts trying to stop the model saying overtly bad things. Implicit bias is much deeper, baked into the model's internal representations learned from patterns in the massive, often biased web data it was trained on. It's unconscious statistical associations.
Like stereotypes learned from the data.
Essentially, yes. The LLM implicit bias method technically probes these subtle word associations inside the model's numerical embeddings, kind of like a digital version of human implicit association tests. LLM decision bias looks at how these internal biases manifest in the model's behavior when faced with certain scenarios. That Julia Ben example is classic GPT-4 implicitly steering towards gender stereotypes in a business context.
So these methods try to peer inside the model's learned correlations.
Exactly, to reveal these subtle, learned biases that surface-level filtering often misses.
That's quite concerning. What are the deep technical challenges in actually removing these ingrained implicit biases, especially when they come from the web data itself? Are there promising new technical approaches?
The deep challenge is that these biases are tangled up with genuine knowledge and language patterns. Trying to surgically remove the bias without damaging the model's overall performance or understanding is incredibly difficult. You pull one thread, and other things unravel. New technical approaches being explored include much more sophisticated data curation and filtering before training, debiasing techniques applied during pre-training, and advanced fine-tuning methods afterwards. The report mentions one called Targeted Latent Adversarial Training. It actively tries to find and fix the model's weaknesses and biases during training.
How effective is that?
Apparently, it can cut the computational cost of removing harmful behaviors by 700 times, while mostly preserving performance on normal tasks. Sounds technically very promising. Other ideas involve maybe more modular architectures where bias components could be isolated, or building explicit bias filters into the model's output path.
Moving to factuality. New benchmarks like Google's FCTS grounding and OpenAI's Simple QA are trying to rigorously evaluate truthfulness. Simple QA uses over 4,000 short, tough, factual questions. And the best model, OpenAI's O1 preview, only got 42.7% right.
Yeah, that 42.7% is a sobering statistic. Shows how hard pure factual accuracy is.
And some models, like Claude 3, just refuse to answer 75% of the Simple QA prompts.
That's also technically interesting. It suggests they're being trained with stronger uncertainty mechanisms or safety guardrails. If the model isn't confident, it prefers to say nothing rather than potentially hallucinate an incorrect fact.
So how do these benchmarks work technically? FCTS grounding versus Simple QA.
FCTS grounding evaluates longer, more complex answers against provided source documents, often using other AI models to help score the faithfulness and accuracy. Simple QA uses short, direct questions requiring specific factual recall, like, who won the Nobel Prize for X in year Y? It directly tests knowledge retrieval. The low scores, even on Simple QA, highlight that LLMs are still primarily pattern matchers, not perfect knowledge databases. Generating plausible text is different from retrieving verified facts reliably.
So why do they still struggle so much with straightforward facts, given all their power? And what technical fixes are needed?
They struggle because their core training objective is usually predicting the next word statistically, not verifying truth against an external reality. Facts can be complex, contradictory in the training data, or just get averaged out during training. Technical fixes likely involve much tighter integration of retrieval augmented generation, RAG. That means the LLM actively queries external trusted knowledge bases in real time before answering, grounding its response in verified information.
So they become better at looking things up.
Essentially, yes, turning them from knowledge approximators into more reliable knowledge integrators. We also need better internal knowledge representation within the models themselves, maybe more structured knowledge, and definitely better ways for them to signal their own uncertainty accurately.
Let's wrap up this section by circling back to data access and transparency. We mentioned the data commons shrinking as websites use robots.txt, terms of service updates, to block AI scraping.
Right, those technical and legal mechanisms are significantly reducing the pool of fresh, diverse public data for training future models.
Impacting diversity, alignment, scalability, exacerbating that data bottleneck.
Exactly. It potentially forces developers towards relying more on internal, potentially less diverse or more biased data sets, or investing heavily in synthetic data.
And transparency. The Foundation Model Transparency Index shows scores improved from 37% to 58% on average between late 2023 and mid-2024, but still lots of room for improvement.
Yeah, improvement, but still far from fully transparent.
In that figure again, over 60% of notable models in 2024 launched without their training code.
Right. So transparency technically means sharing details about data sources, algorithmic choices during training, deployment practices, evaluation results. Withholding the training code specifically makes it really hard for the technical community to independently verify claims, replicate results, understand failure modes, or build directly upon the work in an open way. It limits scrutiny and slows collaborative progress.
So final thoughts on this section. Will data restrictions inevitably push AI towards proprietary data in closed ecosystems, or will synthetic data techniques ride to the rescue? And can we technically enforce or incentivize more transparency?
I suspect we'll see both happen in parallel. Data restrictions will definitely push some towards more proprietary data silos, especially where data is a key competitive asset. But it will also pour fuel on the fire for developing much better synthetic data generation techniques, sophisticated simulators, maybe new ways to generate truly novel, diverse data without just copying biases. As for transparency, technical enforcement could involve things like standardized metadata requirements for models, forcing disclosure of key training details in machine-readable formats. Incentives could range from public recognition for open practices to maybe even regulatory benefits for companies meeting higher transparency standards. Finding that balance between fostering competition and enabling open scientific progress is the key challenge here. Hashtag outro day.
Wow, what an absolutely packed deep dive into the technical heart of AI today. It really feels like we're seeing these dual narratives playing out simultaneously. On one hand, incredible acceleration in technical performance, those plummeting costs, the hardware gains, models hitting superhuman levels on specific tasks.
Yeah, the raw capability growth is just astonishing. Language, vision, robotics breakthroughs happening constantly.
But on the other hand, these growing technical challenges,
Hmm.
the data bottleneck becoming very real, the persistent problem of implicit bias needing sophisticated techno-fixes, the ongoing struggle for true factual reliability.
Exactly. Models get bigger, faster, more capable, but the underlying technical hurdles around robustness, common sense, data scarcity, and responsible deployment are becoming clearer and more critical.
It's this constant tension between scaling up capabilities and ensuring control, robustness, and trustworthiness from an engineering perspective.
Absolutely. The demand for data outstrips supply, pushing innovation in synthetic data. Hardware leaps forward, but power consumption becomes a new wall, demanding new energy solutions. Capabilities soar, but bias and factuality remain thorny technical problems. It's a really dynamic push and pull.
So let's leave our listeners with a final provocative thought to chew on. Given these exponential advancements, but also these clear technical bottlenecks, data scarcity, the difficulty of robust reasoning, what kind of fundamental paradigm shift in AI architecture or learning might we anticipate? Could we see a technical leap in the next decade that maybe bypasses the need for quite so much data, or integrates true common sense more natively?
That's a multi-trillion-dollar question, isn't it? Maybe a shift away from purely statistical learning towards models that build more explicit, causal, verifiable world models from less data. Or perhaps truly hybrid systems that effectively blend neural nets with classical symbolic reasoning and knowledge bases, getting the best of both worlds.
And maybe the flip side, what unforeseen new technical problems might emerge from this continued scaling and complexity that we aren't even thinking about yet?
As AI systems become more autonomous, more interconnected, maybe challenges in debugging emergent system-wide failures across networks of interacting AI agents, ensuring long-term stability and resilience in complex, evolving, potentially adversarial environments. The complexity itself could become the problem. It's definitely an exciting and technically very challenging frontier ahead.
Truly is an exciting and complex future for AI, and for all of us trying to understand its technical underpinnings as it evolves so rapidly. We really encourage you, our listeners, to keep digging into this fascinating technical landscape and consider the deep implications for your own work and interests. And just one last reminder, to stay updated on the latest AI and ML research papers we discuss, do check out the Neural Intel webpage. The link is right there in the bio.
Thanks for tuning in.
Until next time on The Deep Dive, keep digging deeper.